بسم الله الرحمن الرحيم الحمد لله كفى وسلام على عباده الذين اصطفى أما بعد. So today we are going to take XC8 tutorial. So in the previous labs we have seen programming with the assembly language. So what happens when we write a program in assembly language? So each instruction in assembly language has a corresponding hex code, a machine code, and the collection of all these machine codes is saved in a hex file, and that hex file is downloaded to the microcontroller. Now when we write a program in C, the same procedure has to take place. The C program is first converted to assembly language, and then the compiler converts that to assembly language, and from there it converts to the hex code, and that hex code of the hex file is downloaded to the microcontroller. Now, what is the advantage of using C instead of assembly? The advantage is we can write a complex program very easily using a high-level language. For example, here it shows you this program, this C program is first converted to its assembly code, and then the compiler converts that to the assembly code, and then it generates the hex file. And this hex file is downloaded to the microcontroller. Now this is the example of this is the advantage of using a high-level language. Here we can see this program. It is only a single line program which multiplies two 16-bit numbers. We have integer A, integer B, and the result. So we have two 16-bit numbers. They are being multiplied here. And if you want to write a similar program for PIC16 microcontroller using assembly, PIC16 does not have a multiply instruction. So if you want to write a similar program using assembly, we have 4 pages of instructions. So we can simplify all of that in C by simply using the multiply instruction, or by simply using the multiply operator. Now let us look at a basic structure of a C program. So like any other computer program, we have to start writing our program using comments. So we write comments in the beginning of the program, and in C we can have multi-line comments written with /* and ending with star and slash, and you can have single line comments by using /. So at the beginning of the program we write a few comments to describe what this program is about, and then we'll have a few preprocessor directives like #include xc.h. Now xc.h is a header file which is part of the XC8 compiler, and this header file, it defines the internal architecture of a microcontroller, of a PIC microcontroller. Similarly, we include another header file known as stdio.h, which is standard input and output header file, and the third header file included here is the config.h. Now this configuration header file, it contains the configuration bits that we define using the configuration bits table in MPLAB X. So this header file, you can see the difference between writing this header file and the previous header files. xc.h and stdio.h, these are built-in header files which are already there available in the compiler, the XC8 compiler. So they are written using the angle brackets. So they are included using the angle brackets. And config.h is a user-defined header file. It is not a part of XC8 compiler. So we are writing this header file, and we will save this header file in the same folder where we have our main project, or the MPLAB project, and this header file is written in double quotation mark as we see here. So these are some of the header files that we include in our main program. And if you want to define any constants, we can use #define directive and define them in this way. So here we are defining the crystal frequency. This is a constant that is required for this delay function. So this double underscore delay underscore ms, this function is once again a built-in function in XC8 compiler, and it needs this constant, crystal frequency constant, and we have to define the value of the crystal frequency, or the oscillator frequency, and we are assuming it to be 8 megahertz here. Then we have a few examples of global variables. For example, unsigned integer I and j and character ch and a string of 20 bytes. And then we have the main function. So these were the processor directives and these were the global variables. Now we have the main function here. So in a C program, the program execution starts with the main function. So this void is the return data type. Main does not return anything. So we are writing void, we write void here. Then main is the name of the function. And when we have brackets in front of that, that means this is a function. So here we start the main function and this is the body of the function. We'll see in the next slide. So this is the main function. So void is the type of the function and this is the function name, and we don't have any parameters in the main function. If we have any parameters for user defined functions, we can include them in the brackets, and this indicates the start of the function. Then inside the body of the function, we'll write all the commands or instructions that we need, and the closing bracket is given here to close this function. Now inside the main function, we write the C statements as we have written before in assembly language. So here tris b equals 0, it clears tris b register, and port b equal 0b010. So these are the values that are copied to the port b register, and these are the initial configurations for input and output and the initial data. And then we have a while loop. A while is a loop, and since we write here 1, that means this is an infinite loop. So 1 is always true. So this is an infinite loop, like how we write in assembly by using go to back or go to main. So we have an infinite loop here. In this loop, the microcontroller keeps on executing these instructions. So this instruction is simply toggling all the bits of port B register, and then we have a small delay of 100 millisecond. This delay function is a predefined function inside the XC8 compiler, so we don't have to define it separately. So this is a loop from here to here, and then return instruction, and in front of return we don't write anything because void does not return anything. So the main function is not returning back anything, so we simply write return, and then we write a semicolon to end this function, end this statement. So each statement in C must have a semicolon at the end, like how we see here, a semicolon here. Okay, so this is the basic structure of a C program, and this example, it shows you comparison between assembly code and a C code. So previously we have seen the assembly program for analog to digital converter. Hash include P18F4580INC and origin 0. These are preprocessor directives. So in C, we can write similar directives like hash include stdio.h, hash include xc.h, and lcd.h and config.h. So user-defined header files are always written in double quotation mark, and they must be saved in the same folder where you have your MPLAB project. And the built-in header files, they are written in the angle brackets. Then if you have any variable definitions like these in assembly, so in C, we can define them before we write the main function, unsigned integer count, and similarly if you have characters or if you have float, we can define all of them here. They will be considered as global variables. Now we start our main program from here. So in the main function, void main, oscillator control equals, so in assembly, we have to write two instructions to copy any data to a variable or to a register. Move LW0x73 and move W to F oscillator control. In C, it is much easier. You can simply write OSCCON equal 0x73. So data is directly copied to this register. Similarly, clear F CLRF tris B. In C, we can simply write tris B equal 0. And here BSF tris A comma 0, bit number 0 of tris A is 1. So in C, we can write tris A 0. So this indicates that it is bit number 0 of tris A register equal 0. Or this must be actually equal 1, not equal 0. This is a mistake here. It should be, because we are using BSF instruction. So this must be tris A0 equal 1. Then we have move LW0x01 and move W to F AD control 0. So AD control 0 equal 0x01. So this is the name of the register AD control 0. Similarly, AD control 1 equals 0x0E, AD control 2 equal 0x1717. And since we have a continuous loop here, back and go to back here, we can write infinite while loop while 1, and we start our VDC conversion here by setting go bit. So BSF AD control 0 comma go. In assembly in C, it is written as AD control 0 bits dot go, which is name of the bit, equal 1. Then we have to wait for go bit to become 0. BTF skip if clear and go to $-2. So this is a loop which waits for go bit to become 0. In C, we can write a while statement for that. So while AD control 0 bits dot go, and this bit is already 1. So this condition is true, it is 1. So as long as this condition is true, as long as this bit is 1, it continues to execute this while loop. So this while loop does not have a body, so there is just a semicolon here. So it is only a condition. So it's only a condition check. So it keeps on checking this go bit. As long as this go bit is 1, it keeps on executing this while loop. Once this go becomes 0, this condition becomes false and it exits the loop. It comes out of the loop and it comes here and move FF AD result high byte comma latch B. So AD result high byte is copied to latch B register. Similarly, latch B equal in C, latch B equal AD result high byte. So we can copy the result directly like this in this way. Underscore delay underscore ms. This is a built-in function in XC8 compiler. We don't have to write a separate delay loop or a separate delay function in XC8. So we close the while loop here and we write a return instruction without anything. So it does not return anything actually, and we close the main function. So this is the complete main function until here. So this is how we can write a simple program using a C program using XC8 compiler. Now let us look at the data types and formats in C language. So this is very similar to what you have already studied in Java. So we have character data type. These are the three main data types that we have. Character, we have a character data type which can store 8-bit numbers. So the data can be stored from 0 to 255, and the default type of a character is unsigned. So by default, if you simply write character, then you can store positive numbers from 0 to 255. And if you want to store negative numbers as well, then you have to include, or we have to write a signed prefix. And when you have signed character, you can store positive as well as negative numbers. Similarly, you have the next data type, which is integer. Integer by default, they are signed numbers and they occupy 16 bits in the memory, and you can store numbers from -32 kilo to +32 kilobyte. And if you want to store only positive numbers, then you have unsigned integer. Unsigned is a keyword that you write as a prefix before integer. So if you write unsigned, if you have unsigned integer, then you can store positive numbers from 0 to 65535. And if you want to store 8-bit numbers, you can use the keyword short. And if you want to store 32-bit numbers, you can use long keyword. Similarly, you have float and double. They are used to store floating point numbers, and they occupy 32 bits in the memory. And whenever we declare some variables, the variable names can be written using alphabets, capital and small letters, and you can have numbers in the variable name, and you can have underscore in the variable names. Variable names cannot start with a digit. You have to start them either with a underscore or with a letter. And function and variable names, usually they contain lowercase characters, and if you have constants, we use capital letters for that. And there are some keywords, there are some fixed keywords in the compiler which cannot be used as variable names. And here you can see some examples. Unsigned short count. So this count is a variable which can store 8 bits, so it is a 1-byte number. And signed integer temp. So signed is not required, it is redundant. So if you simply write integer temp tmp, then it is a signed number which can store positive and negative. So you don't have to write signed here. Similarly, float pi and character ch, and this will become a string of 5 bytes. If you simply write character ch, then it is a single byte with only 8 bits. And if you write in the brackets, if you write a size for a character, then this becomes an array of characters, so it becomes a string. Now these are the different data formats that we can store. By default, if you write any number in C, it is considered as a decimal number. And if you want to use hexadecimal numbers, then you have to use the prefix 0x. And for octal numbers, you have to use the prefix 0. And for binary numbers, you have to use the prefix 0b, and you have the bits, 8 bits. There are some more examples given here. Integer a and m. So if you have multiple variables of the same data type, then you can write them in the single line. So you have a and m, both of them are integer, and character ch is a single character, and short I equal to, you can define or you can assign an initial value to any variable. So here I has an initial value of 2 and k has an initial value of 5. Unsigned integer get 1, float pi equal 3.14. This is again an initial value, and character string 10. Now this str is a variable, is a character variable of 10 bytes. So it occupies 10 bytes in the data memory. So in the data memory, when we store this string, the microcontroller will reserve 10 bytes for the string character, and out of these 10 bytes, it will assign these values. So MIKROC, 6 bytes are filled in the data memory, and the remaining 4 bytes, they are empty. Now we have the main function here, a equal minus 10. So this is an example of decimal number. M equals 0, 1, 6, 5. This is an octal number. Character a equal character ch equal a. Now if you have a single character, then they are written in single quotation mark. If you have strings, they are written in double quotation mark. I is a hexadecimal number, k is a binary number, k is a binary number, and get 1 is again a decimal number. Now if you want to change individual bits in any register, then we can write name of the register bits dot name of the bit. So intcon is name of the register, bits dot GIE is this bit number 7, and we can also write the name of the bit directly. So GIE is name of the bit equals 0 without writing name of the register. Once again, if you simply write the name of the bit directly, XC8 compiler, it identifies where this bit is from and in which register this bit is saved, and it can access the bit or it can change the value of the bit. Similarly, latch C5, which is for bit number 5 in latch C register. In C, arrays are written in this way. So this is an example. Unsigned character calendar. Calendar is an array of characters, and it has 12 characters or 12 bytes, and you can assign the values in this way using the curly bracket, and each element of this array is separated by a comma. And if you have multi-dimensional arrays, they are written in this way. So here you have number of rows, and here you have the number of columns. So it has 2 rows and 3 columns, and each row is enclosed in curly brackets, and each row is enclosed in a curly bracket and separated by a comma, like this. And the whole array is also enclosed in curly brackets as shown here, and then you have a semicolon to end the definition of this and the assignment of this multidimensional array. There is no string data type in C language. Instead of that, we use the character data type. So we use character data type and name of the variable and then the size of this string. So if we assign it in this way, then in the data memory, the compiler will reserve 10 bytes for this str. And sometimes if you want the compiler to dynamically assign or reserve the values or reserve the size of this string, then we can keep the bracket empty. And at the time of definition itself, we can specify the data in this way. So here in this example, the microcontroller will reserve 5 bytes or 6 bytes in the memory. So 5 bytes are taken by this data EE366, and at the end there is a null character. So if you want to specify byte by byte, then at the end of the string there must be a null character. This is known as a null character. Now this null character it indicates end of string. It indicates that the string ends here. So each string must have a null character. Each string must have a null character. So if you are assigning the values in this way, byte by byte for a string, then you have to specify the null character by yourself. But if you specify the data of the string in double quotation mark, then you don't have to specify, you don't have to write a null character. Microcontroller or the compiler will add a null character on its own at the end of this. Now let's look at operators and operands. Here we have example of shorthand operators or compound assignments. So if you have a single variable and you are performing an operation on the single variable, so you have a single operand. So if you, instead of writing a equal a plus 8, you can simply write a plus equal 8. Similarly, a minus equal 8, a multiply equal 8. This is an example of pre-increment and post-increment. So in plus a is pre-increment. The value of a is incremented first, and then it is used in the expression or in the statement. And in the post-increment, the value of a is used first, and then it is incremented for the next iteration. Similarly, pre-decrement and post-decrement. And these are relational operators: greater than equal, less than or less than equal, and double equal sign to compare whether it is equal or not. And this is for not equal. Logical operators for logical and, logical or, and logical not. Bitwise operators for bitwise complement, shifting left and shifting right, shifting the bits to the left and right. So here 2 bits will be shifted to the left, 3 bits are shifted to the right. And OR and XOR. This slide shows you the variety of different operators. And we have the conditional statements, if statements. So if, and then the condition, if a is greater than m, then it will execute these 2 instructions, and if it is false, it will execute this instruction. So whenever you have multiple statements inside the if, then we can enclose them in the curly bracket like this. And if you have a single statement, then there is no need of curly bracket. You can simply write the statement under the condition. So you can write this in this way. You can write it in this way. This is another example of conditional statement. So here you have a condition. If this condition is true, it will execute operation 1. If the condition is false, it will execute operation 2. In this example, if a is greater than b, it will take the value of a, and the value of a will be assigned to the maximum. And if this condition is false, it will take the value of b and that is assigned to the maximum. Then you have a switch statement, which is another type of conditional statement. So you have a switch selector, and you'll have multiple constant cases. So depending on the case values, it will execute one of these statements. So you can see an example here. So if the value of I is 1, it will execute case 1. That means it goes here, it will execute this statement. And if the value of I is 2, if the value of I is 2, it will come here and it will execute this statement. And if the value of I is anything other than 1 and 2, it will execute the default statement like this. Suppose sometimes if you don't have a break statements, so if you miss or if you forget to write a break statement here, then what will happen is, if the value of I is 2, it will execute this statement, and it will continue. It will also execute this statement, and it will keep on executing as long as it does not find a break. So when it finds a break, then it comes out of the switch statement. Then we have loop statements. We have a while loop. So in a while loop, it will check the condition here first, and then it goes inside the body of the loop, and it will execute the instructions inside the body of the while loop. In a for loop, you have the initial value and the condition and the post decrement or increment. So after executing, so first it assigns, before entering the for loop, it will assign the initial value. Then it checks the condition. If the condition is true, it will execute the loop, and after executing the loop once, it will execute this statement. Similarly, in a do while loop, it goes inside the loop, it will execute all these instructions, and then at the end of the loop, it will check this condition. If this condition is true, then it will keep on executing the loop. And in the do while loop, at the end, you have a semicolon. You have a semicolon at the end of a do while loop. In a while loop, you do not have a semicolon. So you have to notice one thing here. In a for loop, you have an initial value and a post increment and post decrement. Whereas in the while loop, you don't have anything. You don't have the initial value and a post increment or decrement. So whenever we use a while loop, we must assign the value of A before we enter the loop. So for example, we must write here before entering the loop, A equal 5, for example. So this is what we are writing before we enter the loop. And before we close the loop, inside the body of the loop, we must have a post increment or decrement statement like this. Similarly, in a do while loop, once again, before entering the do while loop, we must assign the value of A, and before the end of the do while loop, we must write the increment or decrement statement. And there is another example given here on this side. In assembly language, whenever we use loops in assembly language, we use a go to statement or a BRA statement. So we can do the same thing here as in C as well. We can write a label like this, and we can write a go to statement to go back to this label. So once again, this becomes a loop. So inside a loop, if we write a continue statement, it will skip the remaining instructions. It will skip the remaining instructions and will continue from the beginning of the loop again. But if you write a break statement, it will stop executing the remaining instruction, and it will go back to the beginning of the loop. If you want to write user-defined functions in C, they are written similar to how we write the main function. So we have the return data type of a function, and this is the function name, and inside the bracket we have the parameters that we are passing to the function, and this is the body of the function, in which we define the statements, or we define the function and we write the statements that should be executed inside this function whenever this function is called. So since we have a float return type, we are returning the variable v, which is volume, and this v is defined as a float number. So when we write functions, we have a function declaration at the top. So function declaration is simply the name of the function with its return type and parameters and a semicolon at the end. And inside the main function, we call this function. So this statement is a function call. We are calling this function, and then we are defining the function here. So after writing the main, we are defining the function here. So you have two options. Either you can define the function after the main, or we can define this function, before main here itself. So if you define this function before main, then in that case you don't have to write this function declaration. So instead of the function declaration, you can simply define the function before main. But if you define it after main, then there must be a function declaration before the main function. Now let us look at the XC8 compiler, MPLAB XC8 compiler. So to download the compiler, you can go to this website, microchip.com/mplab/compilers. The link was already given to you on Blackboard for downloading the XC8 compiler. You can go to this link and then scroll down, and you will find compiler downloads tab. Go here and click on this download button, and you can download the XC8 compiler. So this compiler is for 8-bit microcontrollers, 8-bit PIC microcontrollers. So download and install the XC8 compiler, and when you start your new project in MPLAB, follow the same steps as we have done before in the previous labs. And on this selection in the compiler, select compiler page. Instead of selecting MPASM for assembly language, now we select the XC8 compiler. So select this compiler and click next, and create your new project. So inside a new project, when your project is opened, right click on source file, click on new, and select main.c. Now we are writing C programs. So instead of assembly, we'll use .c now. So click on this main.c, and it will create a new C file for you where you can write your complete program. So this is an example where you can write your C program. So complete your program, and then build your program. So once your program is built, you can once again you can find the hex file is generated, and you can load this hex file in Proteus, and you can simulate your code. So remember, practice makes perfect. Keep on practicing. Try to practice as much as possible, and that will help you master the C language.